Yeah, so thank you very much for a kind invitation. And yeah, today I want to talk a bit about that what is ongoing research project, I think, for quite some years. So everybody can see my slides, right? I hope.
Yep.
Great.
Yeah.
So the research is actually joint work with also Sir Louis, who is here, partially Professor Streit, who is here, and yeah, generalized Grey Brownian motion can be seen somehow as another version to generalize fractional Brownian motion, or to generalize Brownian motion in a sense, but not going by the Gaussian case, but more like the yeah, fractionalization in the sense of we use a fractional differential integral operators, if you want to say so. Maybe some motivation. I could also take COVID, of course, but I took influenza because the paper is from influenza. That's also somehow I got into this business. There is a quite elaborated paper by Dirk Brockmann, who is also one of the experts that in Germany now for COVID. He is a chief modeler of the RKI, Robert Koch Institute. What he did is they wanted to model human mobility in US, and they did it by checking how the dollar bills are somehow spread in time. So there is this website where you have the $1 bill. You can somehow put the number inside, and then you can see where it was and somehow where in the world is circulating. Yeah. So and they asked a lot of people to do that, and they found out that they have a power tail, and actually they could fit the human mobility by a fractional Laplacian, which was behind that whole thing. Also now, what are the new studies in COVID from him? They can see somehow the same behavior. So you have, because of this, yeah, we know that you go with a train somewhere, and if you have a time scale, typical human time scale, you have some tumbling, and then suddenly you have a jump and something like this. Yeah. So you see that this is, for example, a typical way where fractional differential equations appear, and yeah. So that was somehow some motivation why maybe this could be of interest. I will show later on how this looks in the generalized Grey Brownian motion. Yeah, so it looks a bit different, of course, but anyway, similar in some sense also. So maybe I think that most of you are fractional Brownian motion experts, I hope, or some of them, but I will review some properties. At least those I see on Zoom, they know it. So a fractional Brownian motion is a Gaussian process, or centered Gaussian process. You have here an RD, such that the covariance is given by this expression. So 1/2 t to the power 2h plus s to the power 2h minus absolute value t minus s to the power 2h. If you put h equal to 1/2, exactly, you get the Markov property, a martingale property, because it's actually the Brownian motion. So very well studied. And of course, if you have h non-equal to 1/2, then you have a fractional Brownian motion, which is neither Markov nor semi-martingale even. So that's a fractional Brownian motion. The paths are, so both processes, so the fractional Brownian motion, the Brownian motion are self-similar, of course. So you have a, if you take this time scaling a times t, of course, we know that we can identify this with the absolute value of a to the power h bht. Yeah, this is, I think, known, and we have stationary increments, and both processes here, so they are all known by expectation in second moment. I don't know why my LaTeX made BC, but of course this goes until E. Yeah. And they are Gaussian. So okay, and now we want to generalize this in some fashion. That means we want to keep some properties which are helpful, especially in physics. Yeah. So things that we want to do maybe later on are polymer models with it. So self-similarity could be maybe of interest. Yeah. Stationary increments could also be of interest. So we have to see what can we keep and how we can generalize it in a way. And so generalized Grey Brownian motion is self-similar it has stationary increments, and it's also completely determined by knowing expectation at second moment. So these are the things that are really helping us in computing this stuff. So if you have somehow, if you know how to get the moments by the first and the second moment, there's already a lot of calculus we can use, and maybe if they are very close to the Gaussian case, you can maybe look up what is done in the Gaussian case, which is very well studied, and we can generalize that here. But it's not a Gaussian process. That is what we have to know. Why it's called gray, I don't know. So it's not, we don't have typical white noise behind, but it's called by Schneider, it's called Grey Brownian motion. Yeah. So Schneider worked on this in the 90s, and he was calling this Grey Brownian motion. Here we see now this correspondence to the equation I just showed from the influenza. So we have the marginal probability distribution instead of a time stretched fractional diffusion equation. Yeah, so we have a time stretched diffusion. So we have here the Laplacian inside. Here we have some stretching factor, of course, yeah. And what you get is a slow or fast anomalous diffusion at the end, yeah. Everything which is corresponding to these things can be found, for example, in the works from Mura and Mainardi, and also Schneider in 92, who actually already did something like a version of a Feynman-Katz formula, but at least without potential, let's say. So they could show that we have a similar representation as in the typical for the fractional heat equation and the generalized Grey Brownian motion. So this is now the process we want to analyze, and at the moment we don't know anything about this process except this. So we should maybe start to define it. So what we have is this is maybe the core thing. So we define later on. We will also do this in the calculus, which is behind, which is a white noise type calculus. We can use the characteristic function to define it, yeah. And what we do is we replace the expectation, the exponential by the Mittag-Leffler function. That's what we do here. So immediately you see for beta equal to 1, we will get a Gaussian process back, exactly a fractional Brownian motion. That's why it's really the fractional Brownian motion we have in the generalization as in this class, in this family of processes, right? So we have now a parameter beta, we have a parameter alpha, where alpha is you could also take the Hurst parameter from before, but because it's related to the fractional calculus, you take here alpha between 0 and 2. Yeah, this would correspond to a Hurst parameter between 0 and 1. So whenever you want to talk about the Hurst parameter, divide alpha by 2. That's what you should do. As you see, we have this covariance matrix inside, which is nothing else but that from the fractional Brownian, what we just said. Yeah. So what we have here is a generalized Grey Brownian motion. Is just in this setting, in this sense, generalization of fractional Brownian motion, where we have instead of the exponential function, we have the Mittag-Leffler function. Yeah, and immediately we get a non-Gaussian process. This is sure. And if alpha is equal to beta, these things we will call this just Grey Brownian motion. This is the case that Schneider, for example, looked at. Now, and generalized in that setting that we really have something like a different alpha from a beta. Yeah. So we have two things here, and we will see this in the slides later on. The first thing is that we have a Hölder continuity, as we know, which is given. So maximal Hölder continuity of path is given by alpha. Yeah, like the Hurst parameter and the fractional Brownian motion, and we have a non-Gaussianality parameter, which is this beta. Okay. So now we can summarize some facts. So we have the characteristic functions given by this Mittag-Leffler version of the Gaussian somehow, and then we can check what are the moments doing, just by computing the moment generating. So just by computing the moments, as we know. So you have that the odd moments, they are all 0, and we have that the even moments, they are given by this here, and what we see is that we get a similar asymptotics in T as we get for the Gaussian case, but of course we have here a prefactor which is differing, especially with the alpha, with the beta inside. So the only thing which plays a role in the moments is actually the alpha. The other one is, means the only way. Of course, the other thing is the prefactor, but the asymptotics somehow are dominated by the alpha here. And we can have then also we can compute the covariance between both, which is also like a scaled version of the covariance of fractional Brownian motion, of course. And then also, like, if we have some increment, we can also compute the characteristic function of it. So what you see is we want to keep the thing simple, So I mean, if you generalize too much and you twist too many parameters, then maybe you get lost in parameters. So the idea is we want to keep it as close as possible to the Gaussian case and see what we can generalize. And a lot of formulas, as I said, and as you see now, we can somehow inherit from the Gaussian case, which makes the things a bit simpler. I said special cases for beta equal to alpha equal to 1. So alpha equal to 1 corresponds to a Hölder continuity of 1/2, means Hurst parameter 1/2. We get a standard Brownian motion. For beta equal to 1 and alpha not equal to 1, we get the fractional Brownian motion. Beta equal to 1 is corresponding to the Gaussian case. And for alpha equal to 1, we get some 1/2 self-similar process. So the self-similarity parameter is this alpha. This we have seen. Because I told you this is what is somehow how the second moment is getting in T. This is the alpha. So this alpha parameter, as in the fractional Brownian motion, is nothing else but the self-similarity parameter. And if you have alpha equal to beta, we call this Grey Brownian motion, which was then introduced by Schneider by the name of Grey Brownian motion. So these are the classes you can look at, and of course, for alpha equal to 1, you can try to if you have self-similarity properties in some fashion, you can try to relate that somehow to Brownian motion and see what happens at the end of the day. This could be, for example, again, interesting in things like if you want to do applications in physics, which are a bit more dependent on the Hölder continuity, then this could be, for example, an interesting parameter to look at. If the models are different, or where are they differing actually? But this is still somehow really on a very early stage to go into physics with this process right now, at least for our group. There are some works by Metzler, for example, which I will also cite soon. So you can now use numerical simulations to simulate the path. How did I do that? Well, we used what's called the normal variance mixture. I will come to that point at the end of the day, or at the end of the talk. You actually couple a fractional Brownian motion with something like a random time change, in some sense, and then you know that this isn't distribution. This is actually nothing else but your generalized Grey Brownian motion, and then you see how this process looks like. So for beta equal to 1, alpha equal to 1, as we have seen, this was nothing else but a Brownian motion. And then if you reduce the beta, what happens here is that we get an envelope which is differing much more from the classical one, from the Gaussian one. So for beta equal to 0 or close to 0, we have here a bit more excursions. Here also where it's getting smaller. And what you see here is this is alpha equal to 0.6. So what we get is just the paths are getting rougher. That's the picture what you should have. So of course we have the beta is somehow a parameter which is telling you how how many, let's say, excursions you have here, which are not in comparison, let's say, to the Brownian case. That's what we should have in mind, maybe. Yeah. Of course, these are 1,000 paths. So you don't know anything about 1,000 paths. You have to let this run much more. But this is just to get an image, and that you have somehow a feeling how does a path look like. If I have just a sample path, I don't know if it's a fractional Brownian motion or it's generalized Grey Brownian motion. That's also something which comes from the random time scaling. So I make I roll somehow a die which is telling me, okay, this is your random number. You put this in front of your path, and then you let it run. And that's somehow not helping you really much if you just look at one sample. So you have to look at the whole ensemble. If you do that, then there was a result by Metzler, which is telling you that the process for beta non-equal to 1 is not ergodic. So you can have this ergodicity breaking parameter, which is the variance of the mean square displacement minus the expectation of the mean square displacement square, normalized by it. So you can compute that. I did it together with Sudhuish. How does this look like in our case? Metzler did it actually in a bit more general case. And what you get is this picture of the ergodicity breaking parameter. And it's a not good use for anybody who likes to do simulations. So the process is not ergodic if it's not beta equal to 1. So we have ergodicity in the case where we have Gaussianity. Everything else we have really like it differs in ergodicity. Yeah? So this means that standard techniques with Monte Carlo simulations, we really have to think about that, how to do it here. Yeah. So that's something one should have in mind if you want does simulations for these things. Yeah. So this is still something we are working on to do better and quicker simulations. But we are also not that far yet. So I can simulate this path like I did it here. Yeah. But the question is how many you need and things like that to do the numerics of it. We have not done yet. Ergodicity is broken in this sense. Sorry. So you have a traditionally, so okay, it is broken in the sense that the variance of the mean square displacement minus the expectation of the mean square displacement square is non-equal to 0. That's how it's broken. So the if you have an ergodic process, it should be 0. That's how you define it. Usually, this ergodicity breaking. Right. Okay. Good. That said, come to the analysis part. So there is this group of Martin Krotos. Sudhuish was also inside, and Sudhuish da Silva, who was also participating very, very much in developing this year, and also 2 students, Florian Janert and Felix Riemann, which thought about, okay, we are close to Gaussian. In Gaussian analysis, we have white noise analysis. So it's maybe a good idea to look at something like similar thing in the setting of the generalized Grey Brownian motion, right? So what they did is they considered the same Gelfand triplet as for the white noise triple. So that we take the rapidly decreasing function. So S is the Schwarz test function space, and we have the tempered distributions as the corresponding dual space. So we get this Gelfand triple. And now, of course, by Bochner min loss, you can define easily although there's a bracket missing, they can define easily, and there's I missing here. The characteristic function to be this this Mittag-Leffler function as before. So sorry for this. Here's an I missing. So this is the characteristic function should be the Mittag-Leffler function, or let's say this Gaussian version of the Mittag-Leffler function I said before. So by this you define this corresponding what they said Mittag-Leffler measure in that sense, or Gray noise measure. And then you can start to make a calculus with it. So what this showed is that for any 0 alpha less than alpha less than 2, this process beta alpha t, where we have, yeah, this is the dual pairing L2 limit actually. In that sense, as we know, we define the fractional Brownian motion classically in a similar fashion. So in the white noise analysis, so we have here this fractional differential operator or fractional integral operator applied to the indicator function. So this is an element of the L2 space with respect to the previously defined measure. And indeed, you can show that this is a generalized Grey Brownian motion. Yeah? Again, this M alpha is this operator here. And yeah, if you plug this in the second moment, you exactly get the stuff back that you wanted to have from the fractional Brownian motion, and scaled with this gamma function with the beta in front of. So the second moment and the first moment are coinciding. So we know then immediately, because the generalized Grey Brownian motion is yeah, uniquely defined by the first and second moment, that we have here the generalized Grey Brownian motion. Yeah? So we have here this M alpha is just the left and right left-sided fractional derivative, or a fractional integral of order R of the Riemann-Liouville type. So this was due to Grothaus, Janat, Riemann and Silva in 2014, Journal of Functional Analysis. And now you can start to do a bit analysis with it. So what we did in 2017 was we defined, for example, for the standard Grey Brownian motion. So we have beta equal to alpha, but you can also generalize it from alpha to beta. We could already do, for example, this generalized Ornstein-Uhlenbeck process, where we have just as a typical typical Ornstein-Uhlenbeck process with a driver, which is nothing else but the Grey Brownian motion. And also here you can identify immediately the kernels, so you know how. So you have of this F beta here, you can really get explicit results about that. So we can redefine it as we have done it, for example, in the white noise setting, also for the Grey-Ornstein-Uhlenbeck process. Then in 2016, we met a paper by Harms, actually brought to us by Sascha Demetre from Kaiserslautern. He's now in Linz, and he is working in financial mathematics. And they are usually interested also in generalization of models in the direction of finance. So he found this paper about fractional Brownian motion, which is going back to a very old result, which is giving us an integral representation of fractional Brownian motion in a certain sense. And this we wanted to combine, and therefore, so we wanted to generalize this in some sense to the generalized Grey Brownian motion sense. And by that you can use the normal variance mixture. So you have that generalized Grey Brownian motion, parameters beta and alpha, is the same in distribution as this, what I said before, this random time change in some sense. Yeah, you have an independent positive random variable y beta, which has a probability density function, which is this m beta function here. This is a generalized function, not a generalized function. It's a special function. You can look it up. I don't say too much about this here, maybe. And then you have here x alpha, where x alpha is nothing else but a fractional Brownian motion with Hurst parameter alpha half. That means in distribution, you can represent that really like a version of a random time change. The square root makes sense because y beta is positive. So by this, it's maybe easier to do the simulations. Yeah. So first of all, fractional Brownian motion, you can do a frac lab. There are many different ways of simulations of fractional Brownian motion. You can read books of it. This y beta you can maybe just generate by a standard random generator, because I mean we know what mu beta is, so you can look it up. It's not so easy because as Seluish knows, it's a very tedious function, and you have to see where you do the cutoff and stuff like that. So it's not so really easy, but actually it's somehow, you know, the pathway how to do this. Yeah. So you could do a random generator, and then you can simulate it. Yeah. So if you have a good handle on this one, you can simulate the path. And moreover, you can now start to maybe talk about how to do this fractional Brownian motion. And so what we did is we represented this generalized Grey Brownian motion via an Ornstein-Uhlenbeck process. So what you can do is you can represent the standard fractional Brownian motion by this integral over a generalized, about a standard Ornstein-Uhlenbeck process. And then the only thing what you have to put is the y beta in there. So it's not very hard to show that this is the same in distribution. The proof comes in on the next page, where we have this x is nothing else but this Ornstein-Uhlenbeck process, where this x is here in the stiffness parameter. Yeah, so this is actually a nice representation, because you can go from every generalized Grey Brownian motion you can define as a mixture of infinite many Ornstein-Uhlenbeck processes scaled in a proper way.
Excuse me, can I ask one question? Is it also self-similar process?
Yes, it's self-similar. Self-similar, and similarity parameter is alpha.
Alpha.
Yeah.
So there is only one similarity parameter, alpha.
Yes, there's only one.
Thank you.
So other direction, sorry. Where was it? Here you see it. Yeah. So alpha is a self-similarity parameter.
Thank you.
You have a similar scaling as in the so you can always think about a fractional Brownian motion, and so if you have this here in mind, that this happens in distribution, and this is a fractional Brownian motion, you see that the self-similarity comes from this here. Yeah.
And y does not have any impact in this self-similarity process. Yeah.
That's a good question. I mean, you can really compute it. I mean, by the formulas I just said before, you can really compute it. And this representation here is, for example, shown by Murat. Yeah. Yeah. So I mean, if you go from the standard, definition of the generalized Grey Brownian motion, you can immediately compute it by the moment, right?
Yeah.
So that's how you do it, and then they showed that this is another version in distribution. So
okay.
Infinite dimensional distribution, of course. Yeah. Okay. So here, what is the idea? I just give you the idea. This is actually a result, I think, by Muraev. It's already quite old, and for fractional Brownian motion, it has also been generalized in some senses to finance by Harms in 2018. Was published, I think. So the idea is just that you represent the fractional Brownian motion by this here. Yeah, and afterwards, so you just do some trick by representing t minus s to the power h1 minus 1/2 by this integral expression. Then plug it in, do stochastic Fubini, and then you come to your expression immediately. And that you have to multiply then afterwards with my beta. So this is, I think, it's not so hard. The stochastic Fubini part, of course, you have to show some estimates, but I think for the Ornstein-Uhlenbeck process here, it's, I think, not too hard to see. If you want to look at the proof, of course, I refer to our paper. Maybe I get another citation. I like citations, but yeah, just joke. Okay. Yeah, so we have now this integral representation, which is nice. And we want to go on there if we maybe can, that the main problem is we want to link that to a Feynman-Katz formula where we have a non-trivial potential, right? And we are not so far yet, but maybe we can use this here. So to come back to Gaussianarity could maybe help us in that setting. But this is still work under progress. So work in process maybe. Yeah, so still not done too much yet with this, but we have this representation. Okay, what else can you do with the calculus? So you can do in a similar fashion as we know from the standard white noise setting. We could do the oh wait, I have to check. There was some question in the chat. No, it's a version of GGBM. That's the first thing. And the second thing is the square root just appears because the m beta function is defined in that way. So if you want to compare it, it's the square root of y beta. So this y beta has already been defined, I think, before as the random variable which comes from this m beta function. And what happens if you compute it is actually that you get the square root of y beta. That's why the square root.
That's the non-Gaussian part of the process.
That's the non-Gaussian part of the process.
Yeah.
Yeah. Okay, so now if we go, I told you we wanted to do something like white noise, so we just try to exploit this whole stuff to meta-cluster distribution. So in a similar fashion as the HIDA triple, so you get to Gelfand triple where you have test functions and distributions, generalized functions in the sense of the quadratic distributions in the white noise setting. So what you need for that is this S mu beta transform. Of course, we don't have an Hermite ordering, so that's one of the big problems here. We are in a non-Gaussian setting, and not only in non-Gaussian setting, as we have to deal actually with RPL systems. If you go behind, you don't have this beautiful Fox-based structure as we have in the white noise setting. Yeah. But you can use results by Yuri and I think also by Professor Daletsky to generalize this appel. So the appel systems are applicable for this, and you can just, there's a lot of calculus done for bi-orthogonal systems, and you can exploit it in a similar way. And the first thing what it does is actually you don't have a nice representation in the sense of the big ordered exponential, but at least you have this here. So you call the S mu beta transform is nothing else but the Laplace transform. In this sense, so the dual pairing of a phi in this S minus 1 space with some this is a test function over the expectation of the test function. So you get this expression at the end of the day. And U here is some holomorphic, some nice neighborhood of 0. So the S mu beta transform is, as we know, is topological isomorphism from this S minus beta space to the holomorphic functions. So the space of holomorphic functions at 0. So again, identify two functions which are coincide in the neighborhood of 0. This is like it's the same definition as in the quantitative test function space and quantitative distribution space in the white noise setting. Yeah, and it's here adapted to the Grey Brownian motion by Grothaus, Silva, Janert, and Riemann. So and then you can also define in a similar fashion the integration, where we have here the weak integration. So we have that you need a measure space, you need this this family of functions from S minus beta for all t, and then you can, if you have that the S mu beta transform is measurable and it's bounded in this way, so the integral is bounded, then there exists a phi such psi actually such that you have this is a psi, of course. Yeah. So we have that this one is called the weak integral, and in this sense we can define integration. And one thing what we did with this was we could define in d equal to 1, for example, the self-intersection local time of a generalized Grey Brownian motion for alpha less than 1, that means h less than 1/2, and all betas as an element in the weak sense. Yeah. So this so we have it really like a Mittag-Leffler distribution. So we have also now an analytic object there. Self-intersection local time is an analytic object in this setting. Right. Now we can also do the T transform, which is then the corresponding Fourier transform. In the similar fashion, this is related to the S mu beta transform as in the white noise setting, so as in the Gaussian setting. So here we have just a characteristic function of this phi in some sense. So this is a generalization of that to the Mittag-Leffler distributions. And the characterization theorem, what we just have seen, is holding also for the T mu beta transform as well as for the S mu beta transform. So it doesn't really matter which one I use to characterize them as elements from S minus 1. And then recently I was looking in during my PhD, I was working quite a lot with scaling scaling operators in white noise analysis. And we have here that if we have a linear bounded operator from S prime to S prime and phi in S1 mu beta, corresponding to let's say a continuous version of it, then we can define the generalized scaling operator as putting this b to the omega. Yeah, so we just say sigma b phi of omega is phi of b omega. If we have that, then we can use minimal type arguments to show that, first of all, if we have a bounded operator, then we have that this phi beta is continuous from the test function space to itself. So we are just working on test function, not on distributions here, right? So the arguments are almost the same as in the Gaussian setting. And moreover, we have that S sigma b from phi psi for test functions is also sigma b phi times sigma b psi. Yeah? So this is a bit of work one has to do here, but it works in a similar fashion. And then if you go on, you get something what we call the generalized Wick formula. And so some of you maybe know the Wick formula in white noise analysis. One can generalize this a bit. So this dagger means the adjoint of the scaling operator with respect to the dual pairing. So I can get the S mu beta transform of this for a psi in the distribution space. This is given by the S mu beta transform of something I call a generalized Mittag-Leffler kernel. So what this is nothing else but the Mittag-Leffler function of of -1/2 psi bb star psi. Yeah. So what you get is you really get the same as we had for a generalized Gauss kernel, but it's a generalized Mittag-Leffler kernel which pops up. And here we have an SV beta transform of the adjoint of the of gamma. So this one is nothing else but the multiplication of the test function with B star of psi. Yeah. So in particular, we have again that these the adjoint applied to the indicator function is this Mittag-Leffler kernel, and you get the pointwise product with a test function in this Wick type setting. So we have something like a generalized Wick formula. If we call the so we have a pointwise product of this one is a function s-1. This one is a function of s1. We can get in this fashion. Yeah. So this is a similar theorem we could get out from the generalized Grey Brownian motion as we get for the in the white noise setting also. Right, and that's where we're stuck now. So we have this generalized Mittag-Leffler kernels, and the scaling operators have now direct implications usually in the white noise setting, as we know, to differential operators. I started to do some computations there, but because we have appel systems, it's not so obvious as in the Gaussian setting, of course. And I hope that maybe in half a year I can tell you a bit more about it. So up to now, I hope you enjoyed, and thank you very much for your attention.
Thank you, Wolfgang. Please, any questions?
I have some comment.
Yeah.
Question and comment.
Good.
You see, in the Gaussian case, we have very powerful technique related with Hermite decomposition. Yeah?
Yep.
In white noise calculus and so on, it is very useful technique. In non-Gaussian case, such decomposition is absent, and this is very essential moment. And several years ago, we proposed with Ludwig Streit and other co-authors an alternative approach, which is based on bi-orthogonal systems instead of orthogonal systems, bi-orthogonal systems. It was quite elegant general theory with one difficult moment that we had not much concrete examples how it works, yeah? Gaussian and Poissonian case, but other examples were absent. What I can hope that for your Mittag-Leffler measures, yeah, such bi-orthogonal system we can construct constructively, yeah, to see such object. What do you think about?
Yeah, that's exactly what I said already, Yuri. So we use these appel systems. Exactly that what you just said. I mean, I mentioned that twice in the talk maybe. So yeah, we use these appel systems actually at the end, and they are constructed, I think, by Seluish and Florian Janat and so on. So they have already the construction of it. So they are eligible. So they showed that
appel system will give you test functions, yeah?
Yeah, but they have P and Q. So they have both.
Yeah.
They constructed both. And the funny thing is that the Q looks like some version of a generalized Gorohot type. So and that's why also these computations what I just showed you went through, because what you have to do if you do this in the chaos decomposition, it's you have to really check on the test function side and then also on the other side. But because it almost looks the same, it's really like a lot of computations went through. Yeah.
So I hope it may be useful, really.
I think one should definitely look into this, and especially if you want to go to the direction of differential calculus in this direction. So I mean, what happens, for example, to a sense of a Malyan or a Hida gradient here? and what happens in the distribution space, because on the test functions, everything is more or less fine. Yeah, right.
Yeah.
You can write it more or less down as a polynomial, make some nice approximation. But in the distribution space, so to go to generalizations there is not so easy. And I think that we can exploit the structure really much. And then also discuss about something like transformation groups, which I would like to do very much.
I will be happy if using your concrete form of Fourier transform or Laplace transform, you can have more concrete formulas. Yeah, probably. I hope it is possible.
Yeah.
Thank you.
Welcome.
Yeah, I mean, just to say that actually this measure is one example, a nice example of this, which fits on this bi-orthogonal business. That's right. I mean, of course, but you see, long ago, we did not have such, still this kind of idea. But nowadays, I mean, this was the paper from 2015. And it is really one example where it fits our business about bi-orthogonal things, yeah?
Yeah, I'm very happy that you discovered this.
Yeah. And afterwards, Martin used it in order to prove this, you know, the Feynman-Katz business. Yeah. So that was the idea of this thing. Yeah.
Okay.
But the Feynman-Katz formula, we have still to say that this is for the potential free case. Yeah. So even if you would put there just a time-dependent linear potential, like we do with the T transform, this whole thing collapses.
Yeah.
And this comes for sure from the fact that I mean, the shift operator doesn't look so nice anymore, right? You have an H Fox function as your density. It's not anymore an exponential. So the shift operator is doing something very ugly. And what is somehow the generalized Radon-Nikodym derivative of that? This is nobody knows. So I cannot write it down explicitly. And that's the main problem. So and another problem which you have very often is that a product of Mittag-Leffler functions is not Mittag-Leffler, so you don't have the semigroup property of the exponential function, right? This makes it a bit hard sometimes.
Wolfgang, I have one student question. Why it is obvious if you put in Mittag-Leffler function minus k squared, it will be positive definite function.
That you can compute, right?
Yeah.
This is so you can
when you put minus k squared in exponent, it is positive definite function, it is clear.
Yeah.
But if you put inside of Mittag-Leffler, why it is obvious or not obvious? It is.
Okay.
Why it is positive? Yeah.
I think this example, I think you showed in your paper 93 with Streit. And there, the key point is you write the Mittag-Leffler function in terms of the integral with the density. And then you can go through. But this is one example in your paper. Actually, this was the motivation when I started this.
Yeah, but Sir Louis, it was 30 years ago. I know. I forgot what I did.
Yeah, but you see, the idea is just to represent the Mittag-Leffler function, use the integral representation with some density, which actually is this M beta density.
M beta function, right?
And then you can prove all your stuff.
It is mixture positive definite function.
Yeah, that's it. Yeah, that's it. Yeah, of course.
Okay, thank you.
Thanks to Louis, yeah.
Any other questions?
Yeah, I have a question regarding, I mean, you use the S transform a lot. The T transform, any problems with that?
No, this is just
okay, that's what I thought.
So the T transform, I told you here the T transform.
There it is. Yeah, okay. I just want to make sure, but because now comes the question. The question is, in the Gaussian case, in the white noise case, the mapping S times or T minus 1 times S is a Fourier transform, in the sense that it intertwines between multiplication and differentiation. And has anybody looked at T-1 times S?
Professor Streit, the problem is here, I think, that if I remember this correctly, where the things are defined, you use the chaos decomposition to get back, right? So you for some things you get it.
No. I mean, you don't need that. I mean, once you know the nature of the S transforms, which are these holomorphic blah blah blahs, then, and if T is invertible, then you can go back from the holomorphic blah blah blahs to the original distributions. But you don't go back by S-1, you go back by T-1.
I mean, as I said, you can, okay. I mean, for some explicit examples, you can try that. Yeah, I think that nobody looked at it yet.
Yeah, that's what.
Yeah, I think this is not explored. No.
Yeah, just put it into the book of crazy ideas. But in the it plays an interesting role in the Gaussian case. And since one wonders what happens when you go off Gaussian, so one might ask that question.
Yeah.
Okay, any other question? I have a question which might look partially off topic, but I believe it is very relevant. You know, we all know many expressions related to fractional calculus, fractional operators. I did recently a very simple thing. I had a fractional Laplace operator. I differentiated with respect to, I mean, actually I have had an equation, the dynamic equation, and I decided to use a fractional Laplace operator. I differentiated the equation second time, with respect to fractional time, and then set it to 0. On the one hand, I should be back to normality. On the other hand, I had some non-trivial dynamic, the second order derivative, so to say. It's like acceleration. So, and while I'm watching Wolfgang presentations, I always tried, to differentiate these expressions and set the fractional parameter to 0. There are still non-trivial non-trivial expressions. What would it mean? It looks like, if I would be an engineer, I would say, okay, I have interaction of currents. It's like inductance, interaction of currents through magnetic field. They feel each other. Markov random walkers on the graph, they should feel each other. As soon as a walker start moving, it should feel its neighbor on the other edge of a graph. What happens? There are non-trivial expressions. If I differentiate with respect to fractional time and set fractional time then to 0, this parameter to 0, as if I stay, but nevertheless I feel accelerations. And then, most of the formulas of Wolfgang also allow such a trick. What does it mean? Random stochastic accelerations due to this non-Gaussianity of what? What does it mean? This is a question. So if we assume that there is a fractional world,
what happens there in the case of fractional Brownian motion? So I'm not sure if it's coming from a non-Gaussianity parameter or it's coming from the long-range interaction.
Probably it's yes. Maybe this is a long range rather than non-Gaussianity.
Yeah, I think it's not a non-Gaussianity. So the non-Gaussianity. So I would say that's what Professor Streit is doing a lot with me sometimes when we have time. It's like, so we're looking at Gaussian, fractional Gaussian chains, let's say, and you check the interaction between. So you discretize it, let's say. So you discretize from 0 to n, and then you check what are the forces given by all the particles, right? And you have this long range interaction, and this comes from the fractional Brownian motion. So this is a non-locality which is intrinsically given by the fractional Brownian motion. So it has nothing to do with the non-Gaussianity. And I think that you get a similar picture. So we have done that with Lewis and also Professor Streit recently for how would, for example, such a polymer model look like in the case of the generalized Grey one, and if you take aside this exponential or Mitter-Kleffler function and you just look at the pair interactions, you have this long range interaction. This comes really from this the covariance of the fractional Brownian motion, which you also have inside here. So I think I think it's not coming from the non-Gaussianity. So just my feeling, of course, I would have to compute it.
I completely agree. And in the other examples, I know this is precisely the case. This is a kind of long memory or something,
Right.
but which actually modifies.
I mean,
Even if I don't want to be a fractional, you know, suppose I'm an integer guy. It feels that I mean, it seems that I should feel a kind of acceleration if I assume that it's possible to make this excurse in fractionality and then return back, setting my fractional parameters to 0, but I have a time derivative. I mean, this fractional time derivative inside. What it's not supposed to be. I mean, well, it means like well, it sounds like a magnetic field. That's what I already told you. Interaction of any moving particles. I mean, they should feel each other in this Leibniz picture, or what?
Good question. I would have to think about that.
Well, actually, I considered, you know, simple idea of random walks on graphs. I got this Mitter-Kleffler function with coefficients. These are series of these Markov chains. I differentiate with fractional time. I set it to 0, and then hop, I have that all random walkers started to fill each other.
Okay.
So, okay, that's what I have. So everything in Leibniz picture, everything is related to each other.
Strange. I don't know.
Well, okay, so it's just, you know, maybe just think maybe about what would happen if we try to, yeah. And you have a lot of formulas where if you differentiate it formally with this non-integer parameter, set it to 0 then.
So you mean the alpha or the beta?
Well,
Wait, let me
this
show
beta, I guess. Yeah, what that is.
Okay.
Better, definitely. At least what I remember.
So this one.
Yeah. Okay, so well, just to think about maybe.
I mean, you can. No, I would. This is too. I mean, the question is if you think about the. I mean, what you did is a geometry on a gasket or something like that, or on a graph actually. So you have some certain geometry inside, and that one you maybe get back by this m beta function. I could think about that, so that you get some certain non-locality back because you integrate something out with respect to m beta. But there I would have to look into the formulas.
Yeah.
This is something like the subordination picture, but this doesn't work always.
Well, I agree. I just, but the idea is that fractionality gives us non-locality, and then even if we formally set it to 0 fractionality, non-locality persists in some, at least in some cases.
In the question backwards would be easier. If you have non-locality, what you have to do to get locality? This is also something, if this is possible. I mean, you could think about just gluing a graph together such that you get nearest neighbors.
Yeah. Initially, I tried to formalize what we discussed with Yuri. What if statistically incompatible events cannot happen simultaneously. How the events might feel each other. And then I immediately got this story.
Okay.
Because, well, from my point of view, it's not enough to have a simple increment, monotonously growing time, but also there should be that some events should not happen simultaneously, while other events might happen simultaneously. And then nature will think, I mean, that's what then you have this story. Once you want to write such a dynamics, then immediately you get this non-locality through fractionality.
Let me try to understand this a little bit better, this non-locality. I mean, there's two kinds of things. One, of course, is that, as Wolfgang was mentioning, is the long range of interaction or the long range memory of one sample path. I mean, it remembers where it has been, and it doesn't, either wants to go back or wants to go forward, depending on the Hurst index. But then you said something else. You were talking about being sensitive to another random walker. That's a different story. I mean, there you would compare two sample paths, right?
This is a simple metaphor from physics, because here I have non-trivial, because of this fractionality, I have non-trivial relations between flows along edges. And then what did we have actually in the past? We have capacitance. If we have a circuit and then then currents would feel each other, simply because there is a magnetic field and they are related through magnetic field. So it's the same second time derivative, the same acceleration.
That would still fall into if you have the different edges and the traveling through, that would be the time parameter of one sample, as far as I understand it.
Yes, exactly. Or another example, for no interference in quantum optics, we have a V scheme and the Pauli principle, which prohibits being more than one electron on a state. If I have one transition, another wouldn't happen. So, and then they drive a particular transition with a laser, and another transition is locked. And they have electromagnetically induced transparency for particular frequencies. And this is the same thing. So, well, at least.
Dear friend, you have very interesting discussion, yeah, for special seminar, probably.
Okay.
But may I ask one general question? Can I?
Yes, sure.
Yeah. Question is the following. Prehistory. In probability theory, people like very much Markov processes with invariant probability measures. Yeah, we have a lot of books, results, and so on. But Brownian motion is not in this class, because for Brownian motion, invariant measure is the bad measure. It produces, even for Brownian motion, non-standard situation with central limit theorem and in principle with limit behavior. Yeah, very strange, by the way, comparing with standard situation. Now we have collection of processes which have not at all invariant measures. Yeah, as I understood. Wolfgang, we have not invariant measures because we have not ergodicity. Yeah. Wolfgang, what do you think? If you have not invariant measure, you cannot have ergodicity. If you have ergodicity, you should expect invariant measure.
Yes. So I also think we have an invariant measure.
Yeah. But now a fair question. What's about limiting behavior? What about central limit theorem or law of large numbers and other limiting behaviors for your processes? It should be very non-standard, because all the traditional technique related with asymptotic behavior invariant measures ergodicity will not be applied, yeah? Cannot apply. What about asymptotic properties of your processes? That is one of the central equations in applications, yeah?
Yep.
Of course, I cannot ask immediately answer, but in principle, it is reasonable equation. Limiting behavior of your process in different cells.
Yeah, I think so. About asymptotics, there has been much done by Ralph Metzler.
Yeah.
But for generalized class. So he is talking more about processes with certain asymptotic behavior, which are in the class of this slow and fast diffusions and whatever. So one maybe should look into that. But yeah, to be honest, I have not done anything in this direction with central limit theorem or so. I just don't know. Yeah, I mean, this ergodicity breaking, we really found this paper by Metzler, and then we really tried to check how it is in our setting, and then we found out, well, we don't have ergodicity in that sense. So yeah, but you're right. Actually, one should look at that. It's maybe yeah, it's of high interest, of course. Also, things like fourth moment problems or so. This is also related to that. Yeah, you have things like in the Gaussian setting, it looks almost the same like the moments, but if you don't have this, then the question is, do you get a fourth moment problem or not, or fourth moment theorem?
I think so. Limit behavior should be extremely non-standard somehow. If you look to central limit theorem, normalization may be very crazy and so on. I don't know.
Yep.
Thank you.
Okay.
Yuri, I'm a little bit confused about your kind of identifying invariant measure and ergodicity. Take for example, a harmonic oscillator,
yeah,
but with a barrier at 0.
Yeah.
That can be arranged. I mean, you use for example, Dirichlet form techniques, and you get that. So you have an invariant measure, but it's not ergodic because it depends on whether you start on the left or on the right. You will stay there.
Yeah, so, but I agree with your argument. But concerning processes, what you discussed, it is possible to have invariant measure, or it is absent by definition. Because if you would like to use such processes as evolution of some models, you need, in many cases, information about equilibrium states, if equilibrium states exist or not. If for such processes equilibrium state never will appear, it is another situation. So
you can have more than one equilibrium.
Yeah, equation is
your initial conditions. You run into one valley or in the other.
But question is concerning processes what Wolfgang discussed. Can we expect invariant measures, or we know a priori that invariant measures absent? I don't know. I have no feeling.
Homework problem.
I think so. But Seluish knows that better because I think they worked also a bit on that. I think that there was the idea to do the stochastic quantization of the measure. And that doesn't work because somehow you get something out where you have something like a conditional expectation inside when I have it, but I don't know if this is published yet or whatever. So there are some non-trivial things, and this would maybe indicate that you have really problems with invariant measures. Right, because means stochastic quantization you should have immediately. I mean, if you have an invariant measure, then maybe you can stochastically quantify it.
Yeah, you start from invariant.
Yeah, exactly. And I think that there was something going wrong. I'm not so sure what it was, but I think there was some conditional expectation thing inside where you have some implicit defined function or implicit defined process, and this made it very hard. So I'm not sure if the answer is negative, but I would say that it's not positive yet.
Okay, but it is an important question.
Yeah.
Thank you so much for very exciting, absolutely exciting morning for me and afternoon for you. So we have a lot to think about during the weekend. Thank you. So next time, Yuri, are you going to make a talk about what of two topics you would like to concern next time? I mean, about fractional models for population dynamics and.
But it will be later, yeah.
Mm-hmm.
Not next week. Over.
Because
we have already speaker next week.
Yes. Just a second.
7th of May.
Right.
We have speaker.
Right. We have on the 14th. On the 14th we have Michael Riccardi. Luca, on the 14th,
yeah,
right?
On the 14th of May. On the 14th of May, we have Michele Riccardi.
Right, Michele Riccardi. So next Friday is the 7th of May, and we have nobody for the moment. But Yuri, if you like,
I can speak about fractional dynamics in population model.
Excellent. So
probably it will be continuation of our discussion today also.
Yeah, great. Thank you so much. We are start, you know.
Jim, I will send you abstract.
Thank you.
Okay.
Okay. So you see, we are growing and still running, and we have speakers, which I mean, till the end of May actually now. So, but people just try to a little bit, you know, postpone their talks, but this is normal.
I would like to say that part of our participants will have Easter on Sunday.
Okay. Yes, sure.
Yes.
And I would like to give my congratulations, for this great day, and for everybody, very nice weekend.
Yeah. Thank you so much.
Okay, see you.
Thank you.